So when we treat an electron transfer in an oxidation reduction reaction, we seek a convenient way to register the movement, to register the shift or delocalization of electron density. So what we're going to do is ride around on each one of these atoms in each one of these molecular structures as the chemical reaction takes place. And we're going to watch from this seat on top of each one of these atoms exactly how that electron distribution shifts in the course of that chemical reaction. And the accounting method that we keep track of this is called the oxidation state of each one of those atoms in that chemical reaction. So in brief, an atom's oxidation state is a positive or negative number relative to a standard state. Well, that means we need to know what that standard state is. But the standard state is defined as an atom in its elemental form. And what do we mean by an elemental form? That means that if I have hydrogen as a free atom, it has a standard state of 0. Its oxidation state is 0. And if I have a free carbon atom, its standard state also has an oxidation state of 0. And same with oxygen, and the same with any other case. So when we have a free atom, that defines the oxidation state of 0. Okay, so let's have some fun with this, and we're going to do this by demonstrating both the redistribution of electron charge and the oxidation state, the results, but we're also going to look at the energy release. And it's this combination of the oxidation state and the shift in that oxidation state in the course of either forming a molecule or in a chemical reaction, and its energy release that we want to keep simultaneously in our mind when we're looking at oxidation reduction reactions. So if we begin with a carbon and an oxygen atom at a distance apart equal to the bond length of carbon monoxide, CO, but with the atoms each in their elemental form, which includes the distribution of electron density around each of the atoms, they'll both have an oxidation state of 0. So let's represent that as our free carbon atom, our free oxygen atom. We'll place that at a distance equal to the internuclear distance of carbon monoxide. We'll define the oxidation state, in this case, as 0, because they are in their free elemental form. And then we're going to proceed to form the molecule. Now, if carbon monoxide is stable with respect to its constituents, carbon and oxygen, then in the formation of that molecule, energy will be released because the potential energy of the structure of carbon monoxide must be lower in energy than its constituent carbon and oxygen. Otherwise, the bond won't form. So we know that we're going to go downhill in energy, and when we go downhill in energy, we're forming the more stable molecular structure. So let's see how this works along with the assignment of oxidation numbers. So if we allow the relative ability of each atom to attract electron density to it in a chemical bond, electron density will move toward the oxygen, and that is, it will delocalize toward the oxygen because oxygen has the greater electronegativity, and in so doing it will release energy. So the oxidation state formalism takes a subtle shift in electron density and turns it into an all-or-nothing statement. And that is, if we now form our carbon monoxide molecule and the electron shift is toward the oxygen, then we're moving 2 electrons from the carbon to the oxygen, and the oxidation state for oxygen becomes -2, and the oxidation state for carbon becomes +2, because we can neither create nor destroy electrons in an oxidation reduction reaction. that says that the electron is transferred from the carbon to the oxygen. That comes back to the statement about all or nothing ownership of that electron, or those electrons in this case. And the analogy is an election. If candidate A receives 51% of the vote, then candidate B receives 49% of the vote. Candidate A is declared the winner. Goes home the successful candidate. It's exactly the same with oxidation reduction. Very, very small shifts in electron distribution separates the winners from the losers. But when we assign oxidation numbers, we assign them exactly that way. There are winners and losers, and they win and lose electrons as units. And it's surprising how crude this is on first glance, but it turns out it's extremely important for analyzing chemical reactions. So, in the case of our carbon monoxide, electron density shifts toward the oxygen, and oxygen is deemed the winner, which is to say the winner of electrons. Even though the shift may be subtle, this provides the oxidation number for the product carbon monoxide. And that oxidation number for oxygen is -2, as we mentioned before. So in an oxidation reduction reaction, we log that in as 2 electrons fully transferred from the carbon to the oxygen. The oxidation number of carbon then becomes +2, and while these are approximate, they, as I mentioned before, provide remarkable insight into chemical reactions, as we'll see in just a moment. Not only into chemical reactions, but in terms of the energy release from chemical reactions. So we've got our oxidation state then of the carbon and the oxygen. We recognize that those electrons are represented by a full transfer. Now notice that you have to be careful about the sign here, because the oxidation state of oxygen is -2. That refers to the charge, not to the counting of electrons, because in fact oxygen has gained 2 electrons. So one form of logic would say, well, I better represent that as a +2. But the oxidation state refers to the charge, the change in the charge. So carbon has lost 2 electrons, so its oxidation state is +2. Oxygen has gained 2 electrons, so its oxidation state is -2. But it's always important to keep track of the fact that this counts the charge transfer. It does not count the number of electrons transferred.